The universe began as a perfectly smooth sea of light and energy. This is one of the greatest scientific puzzles we have ever faced. How could that flawless, empty expanse transform into a cosmos filled with hundreds of billions of galaxies? The answer is hidden in the ghostly tremors of quantum fluctuations, the unpredictable jitters that rule the subatomic world. By the end of this journey, you will understand how microscopic randomness planted the seeds for every single galaxy we see. We will trace how these quantum whispers were stretched to cosmic scales, frozen into the fabric of space-time, and sculpted by dark matter into the grand cosmic web. What invisible hand imprinted the first imperfection onto that perfect canvas? And how can something so random create something so beautifully structured? What does it mean that our entire galactic home might rest on a foundation of quantum chance? That perfect smoothness is not just a scientific fact, it is a profound cosmic mystery. We can see the evidence of this ancient uniformity with our own eyes, or rather, with our most powerful telescopes. They capture the afterglow of the Big Bang itself, a faint microwave light that fills every corner of the sky known as the cosmic microwave background. This light is a snapshot of the universe when it was only 380,000 years old, a cosmic baby picture. And in that picture, the temperature of the cosmos is almost exactly the same everywhere you look. The variations are incredibly tiny, mere ripples of about 1 part in 100,000. To put that in perspective, if the early universe were as smooth as a billiard ball, the height of its imperfections would be less than the width of a human hair. This is the state known as homogeneity and isotropy, a universe that is essentially the same in every direction and at every point. It is the ultimate blank slate. But here lies the paradox. A universe that starts this smooth should, according to the relentless pull of gravity, stay smooth forever. Gravity is an attractive force. It draws matter together, but if every particle of matter is spread out with near-perfect uniformity, the gravitational pull from every direction cancels out. There is no slightly denser region to act as a gravitational anchor, no seed around which matter can begin to gather. It is a cosmic stalemate. A perfectly mixed soup with no clumps should never form meatballs. Yet our universe today is nothing but clumps. Stars gather into galaxies, galaxies gather into clusters, and those clusters weave the vast cosmic web. So the question becomes not just how did structure form, but how did it ever begin to form at all? The flawless canvas had to receive its first, fateful brushstroke of imperfection. The search for the artist who made that mark takes us back to a time before atoms, before light could even travel freely, to an era so early and so extreme that our understanding of physics reaches its limits. This fundamental uncertainty creates a universe that is restless at its very core. Think of it this way. In our everyday world, if you have an empty box, it is simply empty. You can measure it, confirm its emptiness, and that is the end of the story. But in the quantum realm, the very concept of empty space loses its meaning. The Heisenberg uncertainty principle tells us we can never precisely know both the energy of a system and the time over which we measure it. This leads to a startling consequence. For fleeting moments, energy can be borrowed from nowhere, manifesting as pairs of particles and their antiparticle twins. They flicker into existence, dance for an impossibly short time, and then annihilate each other, returning the borrowed energy. This ceaseless, frothing activity is what physicists call quantum fluctuations. It means that what we perceive as a perfect vacuum is, in reality, a turbulent sea of spontaneous creation and destruction. We can even witness the effects of this quantum restlessness in a laboratory. Place two perfectly smooth, uncharged metal plates extremely close together in a vacuum. The space between the plates is so narrow that only certain wavelengths of these virtual particles can fit. Outside the plates, all wavelengths are possible. This difference in quantum activity creates a subtle pressure, pushing the plates together. This is the Casimir force, a tiny but measurable push caused by the ghostly presence of particles that are not really there. It is direct proof that empty space is alive with potential. Now, scale this idea up to the very beginning of everything. In the first sliver of a second after the Big Bang, the entire universe was compressed into a volume smaller than a single atom. Every point of space was unimaginably energetic and dense. In that environment, the quantum fluctuations were not confined to tiny scales. They were everywhere, imprinted on the fundamental fields that make up reality. These were not fluctuations in particles, but in the very fabric of energy and gravity itself. Microscopic patches of space would randomly have a tiny bit more energy, a fractional increase in density, while neighboring patches had a tiny bit less. These random jitters were the universe's first and most important imperfections, but they were ephemeral, blinking in and out of existence far too quickly to matter in a static universe. To become permanent, they needed a cosmic force of unimaginable power to stretch them, freeze them, and etch them into the sky. That force was inflation. This is where the story takes a breathtaking leap in scale. The theory of cosmic inflation provides the crucial link between the quantum world and the cosmos we see. To understand it, think of the universe not as a balloon being blown up, but as a piece of dough with yeast in it. In the tiniest fraction of a second after the beginning, a new kind of energy, something physicists call the inflaton field, took control. This field possessed a strange property. It caused space itself to expand at a rate that is almost impossible to comprehend. The universe did not just grow. It doubled in size and then doubled again and again, over and over, faster than the speed of light. In less time than it takes for light to cross a single proton, the entire observable universe inflated from a subatomic speck to something roughly the size of a grapefruit. This was not an explosion into space. It was the explosive stretching of space itself, and this ultimate stretch did something miraculous to those quantum whispers we just discussed. Those random, flickering fluctuations in the inflaton field were caught in the expansion. A microscopic patch of space that randomly had a tiny bit more energy was suddenly pulled apart, its boundaries stretched to scales larger than galaxies. The jitter that lasted for a fleeting moment was yanked so far, so fast that it could no longer snap back. It was frozen in place, transformed from a quantum maybe into a classical fact. It became a permanent region of slightly higher density, a seed. Inflation acted as the universe's ultimate amplifier, taking the faint, random static of the quantum vacuum and turning it into a foundational roar imprinted across the cosmos. But at the end of this incredible growth spurt, the universe was still a hot, dense, and nearly uniform soup of particles and light. The blueprint for all structure was now written into the very fabric of reality, a pattern of faint hills and valleys in the density of matter. Yet it was just a pattern, a ghostly impression waiting for a force to give it shape and substance. Those subtle hills and valleys in density were the universe's first and most important topographical map. Yet for millions of years, nothing much seemed to happen. The cosmos continued to expand and cool, a vast, dark, and nearly uniform cloud of hydrogen and helium gas, with the invisible scaffolding of dark matter woven throughout. The seeds were planted, but they needed time and a relentless force to grow. That force was gravity. It is the universe's great architect, and its work is patient, cumulative, and inevitable. Every single one of those quantum-imprinted regions of slightly higher density possessed a crucial advantage. Just a fraction of a percent more matter meant a fractionally stronger gravitational pull. In the expanding sea of nearly uniform gas, these spots became gentle gravitational anchors, and here dark matter played its decisive role. This mysterious substance, which does not emit or absorb light and interacts only through gravity, began to respond first. As ordinary matter was still buffeted by the pressure of radiation, dark matter particles, unaffected by light, could quietly slide into these overdense regions. They pooled there, deepening the gravitational wells, making the subtle hills of the quantum blueprint steeper and more pronounced. These wells became the skeletons of future galaxies. Only later, as the universe cooled further, could the ordinary hydrogen and helium gas feel this deepening pull. It began to stream inward, flowing along the invisible contours shaped by dark matter. Imagine a landscape after a gentle rain. The water does not fall evenly. It gathers in the slightest dips and gullies, following the pre-existing shape of the land, carving those features deeper over time. The gas, now caught in these deepening wells, began to swirl and compress. As it piled up, density soared, temperatures skyrocketed, and in the furious collisions at the core of these collapsing clouds, a miracle of physics occurred. Nuclear fusion ignited. The first stars burst into existence, piercing the primordial darkness with their fierce, blue-white light. These were not like the stars of today. They were behemoths, hundreds of times more massive than our Sun, living fast and dying in spectacular supernova explosions that seeded the cosmos with heavier elements. Around these first stellar nurseries, drawn by the combined gravity of stars, gas, and the dominant dark matter, the first proto-galaxies coalesced. This gravitational amplification was a chain reaction across billions of years. Small seeds grew into stars, stars gathered into galaxies, and galaxies, pulled by the same relentless force, began to trace out the grand design imprinted at the dawn of time. They flowed along the ridges of density, forming vast filaments that stretch across the emptiness like threads in a cosmic spiderweb. Where these filaments intersected, great clusters of thousands of galaxies gathered. Between them remained the immense, empty voids. This is the cosmic web we map today, a structure of breathtaking scale and beauty. And every knot in that web, every brilliant galaxy cluster, can trace its lineage back to a specific, random quantum fluctuation, stretched and frozen into the sky during that first incredible moment of inflation. It is a story that connects the smallest rules of reality to the largest structures we can see. But such a grand narrative requires more than just theoretical elegance. How do we know this isn't just a compelling story we've told ourselves? The proof is not hidden in speculation. It is written in the oldest light in the universe, a fossilized echo that carries the signature of those first quantum seeds. The proof is written in the oldest light we can see, that faint, cold glow that fills the void, the cosmic microwave background, is far more than a simple afterglow. It is a fossilized photograph of the infant universe, taken when it was a mere 380,000 years old. For decades, scientists predicted that if the theory of inflation and quantum seeds was correct, this ancient light should bear a specific, telltale pattern. It would not be perfectly smooth. It would be gently mottled like the surface of an orange, with tiny variations in temperature from one patch of sky to another. Finding that pattern became one of the greatest detective stories in modern cosmology. The hunt required instruments of incredible sensitivity, launched beyond the interference of our atmosphere. Satellites named WMAP and later Planck spent years staring into the deep sky, meticulously measuring the temperature of this cosmic background down to a few millionths of a degree. What they found was a revelation. The map they produced is a masterpiece of data, a splotchy tapestry of hot and cold spots scattered across the entire cosmos. And the statistics of this pattern, the way these spots are sized and distributed, match the predictions of quantum fluctuations stretched by inflation with astonishing precision. The pattern is what scientists call scale invariant and Gaussian. In simpler terms, this means the fluctuations look essentially the same no matter what scale you examine, and their distribution follows the classic bell curve of pure random chance. It is the precise fingerprint you would expect if the seeds of all structure were born from quantum noise. This correlation is not just suggestive. It is considered one of the strongest observational pillars supporting the entire inflationary paradigm. When we look at that map, we are not just seeing light. We are staring directly at the amplified quantum jitters from the universe's first moment, frozen into the sky when atoms first formed and light could finally travel free. That map is the smoking gun, the direct evidence linking the frenetic uncertainty of the quantum realm to the majestic architecture of galaxies. Yet, as definitive as this ancient photograph is, it is only a two-dimensional snapshot, a single slice of time. To watch the full story unfold, we must see the universe in 3 dimensions. That ancient light gives us the blueprint, but the building itself is a 3-dimensional cathedral of staggering scale. To see it, astronomers have undertaken a monumental cartographic project, mapping the precise locations of millions of galaxies across vast swaths of the universe. Projects like the Sloan Digital Sky Survey have, night after night for decades, pointed telescopes at the sky, not just to take pretty pictures, but to gather the light signatures that reveal a galaxy's distance. By stitching this data together, they have constructed a 3-dimensional atlas of the cosmos, revealing the cosmic web in all its intricate, filamentary glory. Within this grand architecture, scientists have discovered a ghostly echo, a cosmic fossil of a different kind. It is a subtle, repeating pattern in the spacing of galaxies. If you were to measure the distance between countless pairs of galaxies across the universe, you would find a curious preference. They are more likely to be separated by a specific, enormous distance than any other. This scale is known as Baryon acoustic oscillations. To understand what this means, we have to go back to that hot, dense plasma before the cosmic microwave background was released. In that seething soup, ordinary matter, which scientists call baryons, was tightly coupled to light. Gravity, pulling from the quantum seeds, tried to make the gas collapse inward. But the intense pressure of the trapped radiation pushed back, creating powerful sound waves that rippled outward through the plasma. These were literal pressure waves, traveling at over half the speed of light, like sonic booms in the early universe. This tug-of-war created spherical shells of compressed matter, expanding outward from every single seed. Then, at 380,000 years, the universe cooled enough for atoms to form. The light suddenly decoupled and streamed free, becoming the cosmic microwave background we see. Instantly, the pressure support vanished. The sound waves froze in place, leaving behind spherical shells of matter, like the rings from a stone dropped in a pond but frozen at a single moment. The radius of those shells became a fixed, universal measuring stick. Over the next 13 billion years, as the universe expanded and gravity pulled galaxies together, that preferred scale was stretched by the growth of space itself, but it remained imprinted on the distribution of all matter. So when we look at our 3-dimensional maps today, we see that galaxies have a slight tendency to be separated by this specific, enormous distance, which is now about 500 million light-years across. It is a fossilized sound wave, a standard ruler etched into the cosmos, and here is the crucial link. This BAO pattern is not the structure itself. It is a subtle wiggle superimposed on the underlying distribution of galaxies, the distribution that was seeded by those quantum fluctuations. By measuring this standard ruler at different cosmic times, cosmologists can trace exactly how those initial quantum-imprinted wrinkles have been amplified by gravity over the eons. It provides a second, completely independent line of evidence, one that tracks the dynamic growth of structure, confirming that the majestic cosmic web we map today is the direct, grown-up descendant of the random quantum pattern we see in the infant universe's first light. But what was the force that gave those ghostly blueprints their solid form? The answer lies in a substance we cannot see, touch, or directly detect. Dark matter is the silent, invisible architect of the cosmos. While the quantum seeds provided the faintest of sketches, dark matter provided the gravitational muscle and the deep structural framework upon which every galaxy would eventually be built. Think of it like this: in the early universe, ordinary matter, the protons and neutrons that make up stars and planets, was trapped in a hot, dense plasma, constantly buffeted by the intense pressure of light. It was like trying to build a sandcastle in a hurricane, but dark matter is fundamentally different. It does not interact with light at all. It feels gravity, but it is oblivious to the push and shove of radiation. This meant that as soon as the quantum fluctuations were frozen in by inflation, dark matter could begin to respond. It could quietly, invisibly, start to slide into those regions of slightly higher density. There were no forces to push it back out. It simply pooled there, deepening the gravitational wells. Over millions of years, these pools of dark matter grew, merging and pulling in more of their invisible kin. They wove a vast cosmic skeleton, an intricate network of filaments and halos made of pure gravity. This invisible scaffold became the true foundation of the cosmic web. Only much later, once the universe had expanded and cooled enough for atoms to form and light to travel freely, could ordinary matter finally feel the pull of this pre-existing gravitational landscape. The hydrogen and helium gas began to flow like water finding the path of least resistance, streaming into the valleys and gathering at the nodes of the dark matter skeleton. It was there, within these deep gravitational wells, that the gas could finally compress, heat up, and ignite the first stars. So every brilliant spiral galaxy, every glowing elliptical, every cluster we see is just the visible tip of a colossal, invisible iceberg of dark matter. Its gravitational embrace is what holds fast-moving stars in their orbits and keeps entire galaxies from flying apart. Without this invisible scaffolding, the subtle wrinkles from the quantum dawn would have remained just that, faint wrinkles. They would have grown far too slowly under their own gravity to ever form galaxies within the lifetime of our universe. The entire process would have been a cosmic non-starter. We can see this partnership in action through some of the most sophisticated computer simulations ever run. Scientists program the laws of physics, input the initial conditions from the quantum fluctuations, and add the dominant presence of cold dark matter. When they press start and let the simulation run for billions of virtual years, something remarkable happens. The virtual universe that evolves looks, in its large-scale structure, almost identical to the one we map with our telescopes. Filaments of dark matter form, galaxies coalesce at their intersections, and great voids open between them. The simulation is not programmed to look like our universe, it is programmed to follow the rules of physics. The fact that it so closely reproduces reality is a powerful testament to this duet. It tells us that the story of our cosmos is not one of chance or necessity alone, but a profound collaboration. The random, microscopic jitters of the quantum vacuum provided the creative spark, the initial asymmetry. But it was the relentless, patient gravity of dark matter that provided the structure, the discipline, and the strength to turn that spark into a universe of light. So when you look up at the night sky, you are seeing the magnificent, visible consequence of an invisible partnership written into the first moments of time. The universe remained a silent, dark expanse for nearly 100 million years after the Big Bang. Then, within the deepest wells of those invisible dark matter halos, a new kind of light was born. The story of how this happened is a tale of patient cooling and catastrophic ignition. Ordinary hydrogen and helium gas, having finally decoupled from the radiation, was now free to feel the relentless pull of gravity. Drawn into the centers of the dark matter scaffolds, this gas began to compress, but compression creates heat, and hot gas has high pressure which pushes back against collapse. For true star formation to begin, the gas had to find a way to cool down. It did so by emitting faint radiation as its atoms collided and recombined, a slow, steady leak of energy into the void. As it cooled, it could condense further, sinking deeper into the gravitational wells, becoming denser and hotter still. This process reached a critical tipping point. When the core of a collapsing gas cloud reached temperatures of around 10 million degrees, the hydrogen nuclei within it, moving with unimaginable fury, began to overcome their natural repulsion. They fused together to form helium, releasing a colossal burst of energy in the process. Nuclear fusion had ignited, the first star was born, and the cosmic dark age was over. These first stars were unlike anything in our night sky today. Astronomers call them population 3 stars. They were true cosmic titans, hundreds of times more massive than our own sun. They burned with a fierce blue-white intensity, living fast and dying young in just a few million years. Their light was not gentle. It was a torrent of high-energy ultraviolet radiation that blasted out into the surrounding fog of neutral hydrogen gas. This radiation was so powerful it began to strip electrons from the hydrogen atoms, reionizing the universe for a second time, tearing apart the very medium that had allowed the stars to form in the first place. This epoch of reionization, driven by these first stellar behemoths, fundamentally changed the nature of the cosmos, making it transparent to most ultraviolet light and setting the stage for all future generations of stars. Crucially, these first stars did not form just anywhere. They ignited precisely where the quantum blueprint, amplified by dark matter, had written its highest peaks. The greatest overdensities from the dawn of time became the cradles for the first light. Groups of these colossal stars, all bound together within a single massive dark matter halo, are what we call the first protogalaxies. They were the luminous seeds of the majestic spiral and elliptical galaxies we see today. Their formation was the universe's direct and spectacular answer to the question posed by those initial quantum whispers. It was the moment the invisible blueprint was finally illuminated, the moment potential became reality. The influence of these first stars, however, extended far beyond their brilliant light. Their brief, violent lives ended in cataclysmic supernova explosions. These explosions did two monumental things. First, they blasted the newly forged heavier elements like carbon, oxygen, and iron out into the surrounding gas. These metals, as astronomers call all elements heavier than helium, would forever change the chemistry of the cosmos, allowing future generations of smaller, longer-lived stars and rocky planets to form. Second, the shock waves from these explosions compressed nearby gas clouds, triggering further rounds of star formation and helping to sculpt the early structure of the growing protogalaxy. The stage was now set. The universe was lit, structured, and chemically enriched. The quiet, dark foundation had given way to a dynamic and complex cosmic construction site. That first brilliant generation of stars set the stage, but it did not dictate the final form of the cosmos. The universe began to diversify, creating a spectacular gallery of galaxies, each with its own unique shape and story. This breathtaking variety, from majestic spirals to smooth ellipticals, is not a random accident. It is the ultimate legacy of those first quantum seeds. Not all of those primordial whispers were created equal. The specific properties of the initial density fluctuation, its size, its strength, and its location within the emerging cosmic web, acted as a cosmic DNA, influencing the destiny of the galaxy that would grow from it. Think of the early universe as a vast, uneven landscape of gravitational potential, sculpted by that frozen quantum noise, a region that received a particularly large and pronounced fluctuation. A high hill in the density map found itself in a busy, crowded neighborhood of the cosmic web. Here, gravity had a powerful head start. Enormous amounts of dark matter and gas were drawn in quickly and violently. This led to a frenzy of early star formation, a starburst so intense that it used up the available gas supply in a relatively short cosmic time. Without a steady influx of new, cool gas to form a rotating disk, and with stellar orbits stirred by frequent interactions, such a region would naturally evolve into a massive, round or football-shaped elliptical galaxy. Its stars orbit in all directions like a swarm of bees, creating that characteristic smooth, featureless glow. Now consider a different seed, a smaller, more modest fluctuation in a quieter, more isolated filament of the web. Here, the gravitational collapse was gentler, more orderly. Gas could flow in steadily over billions of years, conserving its rotational momentum. As it settled, it naturally flattened into a spinning disk, much like a ball of pizza dough spinning into a flat crust. Within this stable, rotating disk, spiral arms could emerge, density waves triggering new star formation and painting those iconic luminous patterns. This is the origin story of a spiral galaxy like our own Milky Way. Its graceful structure is a testament to a quieter, more isolated beginning, but the story does not end with a single seed growing in isolation. The cosmic web was a dynamic construction site. Smaller proto-galaxies, each born from their own quantum seed, were constantly drawn together by gravity. These mergers were the great sculptors of galactic morphology. A major merger between two large spiral galaxies could destroy their delicate disks, randomizing stellar orbits and creating a new elliptical galaxy. A series of smaller, gentler acquisitions could feed a spiral's central black hole or add stars to its outer halo without destroying the disk. Even the irregular galaxies, those misshapen, turbulent collections of stars, often tell a tale of recent gravitational encounters or ongoing ingestion of gas. So when we look at Hubble's deep field images, that stunning tapestry of thousands of galaxies, we are seeing more than a beautiful random assortment. We are looking at a family tree, the elegant spiral, the red and dead elliptical, the chaotic irregular. Each can trace its lineage back to a specific variation in the quantum noise pattern from the universe's first moment. The amplitude, the scale, the surrounding context of that initial whisper set a galaxy on a path then shaped by billions of years of cosmic history, collisions, and star formation. The universe's grand artistry, it turns out, has its deepest roots in microscopic randomness. Yet this entire cosmic history rests on a profound mystery. We have traced the journey of quantum fluctuations from microscopic whispers to galactic superstructures, but we must now ask where those whispers themselves came from. Our current understanding hits a wall at the very beginning, in a fleeting moment of time so short it defies human imagination. The first 10 to the power of -43 seconds of the universe is known as the Planck epoch. To grasp this scale, consider that a single second contains more Planck times than there have been seconds since the Big Bang itself. In this realm, the universe was smaller than the smallest subatomic particle, and the energy densities were so extreme that the two pillars of modern physics, Einstein's theory of general relativity and quantum mechanics, collide. General relativity beautifully describes the cosmos on large scales, the warping of spacetime by mass and energy. Quantum mechanics, with its uncertainty and probability, rules the world of the very small. But in the Planck epoch, the universe was both unimaginably small and unimaginably dense. You cannot separate gravity from quantum effects here. Spacetime itself would have been subject to wild, chaotic quantum fluctuations. Our equations break down because we lack a complete theory of quantum gravity, a framework that would unite these two great descriptions of reality. This is the final frontier of fundamental physics. Without it, we cannot truly describe the moment of creation or say with certainty what happened at time zero. Several profound ideas attempt to bridge this gap. Theories like loop quantum gravity propose that spacetime is not a smooth, continuous fabric, but is woven from tiny, discrete loops, a kind of quantum foam. String theory suggests that the fundamental constituents of reality are not point-like particles, but vibrating strings, and that the universe may have more than the three spatial dimensions we experience. In these frameworks, the Big Bang might not have been a singular beginning from nothing, but a transformation, a bounce from a previous cosmic phase. What does this mean for our story of galactic seeds? It suggests that the quantum fluctuations inflation amplified may have been born even earlier, as tremors in the very geometry of spacetime during the Planck epoch. The initial conditions for our entire universe, the subtle pattern of hills and valleys, could be imprinted in the quantum structure of gravity itself. This is a staggering thought. It means the blueprint for every galaxy, star, and planet might be encoded in the most fundamental architecture of reality, written not in particles or fields, but in the quantum geometry of the cosmos. Exploring this frontier pushes human understanding to its absolute limit. It connects the majestic spiral of a galaxy billions of light years away directly to the deepest questions we can ask. What is spacetime? What does it mean for something to begin? While we do not yet have the final answers, the pursuit itself reveals a universe of breathtaking coherence, where the largest structures we observe carry the indelible signature of the smallest possible scales. This journey from quantum foam to galactic web leads us to a final, almost dizzying possibility. The same mechanism that planted the seeds for our galaxies may have also generated an infinite number of other, completely separate universes. This is the Multiverse Hypothesis, a direct and profound implication of the theories we have been exploring. Think back to cosmic inflation, that moment of unimaginable stretching. The leading models suggest that inflation, once started, may be eternal. Picture a vast, bubbling cauldron of spacetime. In most regions, inflation eventually ends, the inflatoned field decays, and a hot, dense universe like our own is born. But in other regions, inflation continues, endlessly creating new space. Within this eternally inflating background, countless bubble universes can pop into existence, each one a separate pocket where inflation has locally stopped. Each bubble is causally disconnected from the others, forever out of reach beyond an ever-expanding horizon. And here is where the quantum nature of the seeds becomes absolutely central. Recall that the specific pattern of fluctuations in our region was a random quantum outcome. In a different bubble, the quantum dice would have rolled differently. The inflatoned field would have decayed at a slightly different energy level, or the random jitters would have had a different amplitude. This could lead to a universe with fundamentally different properties. The constants of nature we take for granted, the strength of gravity, the mass of an electron, the number of spatial dimensions, might be different in other bubbles. Some bubbles might have physical laws where atoms never form, or where gravity is so strong that any structure instantly collapses into black holes. Others might be so smooth and empty that not a single star ever ignites. In this breathtaking view, our entire cosmos, with its hundreds of billions of galaxies woven into a vast web, is not the universe. It is simply our universe, one particular realization frozen out of an infinite quantum lottery. The majestic structure we call home was not predetermined. It was one possibility among a near infinity of others, a single cosmic story selected by chance from the quantum noise at the beginning. This idea remains highly speculative, a frontier of thought rather than established fact. There is no known way to observe or test for these other bubbles, as they exist completely outside our spacetime. Yet, as a conceptual framework, the multiverse shows just how far-reaching the consequences of quantum seeding truly are. It challenges our deepest intuitions about uniqueness and causality. It suggests that the ultimate reason our universe looks the way it does may not be due to a single, elegant, necessary law, but to the random outcome of a process that generates endless variety. Our galaxies, and we who observe them, are the beneficiaries of a particular roll of the quantum dice in a cosmic casino of unimaginable scale. The sheer explanatory power of inflation makes it a cornerstone of modern cosmology, but it is not the final word. Every great scientific theory must face rigorous scrutiny, and the story of our cosmic origins is no exception. While inflation elegantly links quantum noise to galactic seeds, some physicists argue it may be too elegant, raising new questions even as it answers old ones. One significant critique centers on the concept of fine-tuning. For inflation to produce a universe that looks like ours, the properties of the hypothetical inflatoned field must be set with extraordinary precision. Its energy must be just right to drive rapid expansion and then decay smoothly into the hot soup of particles. To critics, this need for such specific initial conditions seems to replace one mystery with another, a cosmic coincidence that demands its own explanation. This has spurred the search for alternative pathways to structure. Could the universe's initial wrinkles have come from something other than an inflatoned field? One intriguing proposal involves cosmic strings. These are not strings in the everyday sense, but hypothetical, incredibly dense one-dimensional defects in spacetime, thought to be remnants of symmetry breaking in the early universe. Like cracks forming in ice as it freezes, these strings could have stretched across the cosmos, their immense gravity warping space around them and creating the density variations needed to seed galaxies. Another class of models suggests a bouncing universe, one that cycles through periods of contraction and expansion. In such a scenario, the quantum fluctuations from a previous cosmic phase could be imprinted onto the new one, providing the seeds without a singular beginning or a period of inflation. The true test for any theory, however, is not its conceptual appeal but its ability to match what we observe. This is where inflation has demonstrated remarkable resilience. The alternatives must account for the same exquisite details we find etched into the cosmic microwave background. They must reproduce that specific, random, Gaussian pattern of hot and cold spots, and they must explain the vast, smooth expanses and the overall flat geometry of the universe, known as the horizon and flatness problems. So far, no alternative has managed to do all this with the same comprehensive simplicity as inflation. Its strength is that it solves multiple, seemingly unrelated cosmic puzzles with one sweeping mechanism. It tells a unified story where the large-scale smoothness and the small-scale structure arise from the same event. The scientific journey, therefore, is far from over. The next chapter will be written not by philosophical preference, but by new data and unique predictions. Researchers are actively searching for signatures that could definitively prove or challenge inflation. One key target is the pattern of gravitational waves from the universe's first moment. Inflation should have generated a faint, primordial hum of these spacetime ripples, which would leave a distinctive curl pattern in the polarization of the cosmic microwave background. Detecting that signal would be a smoking gun for inflation. Other theories might predict different signatures in the distribution of galaxies or the presence of exotic relics like those cosmic strings. The process is a beautiful example of science at work, where competing ideas are sharpened against the whetstone of observation. Our origin story is not a finished book, but a living manuscript continually edited by the light from the dawn of time. The quantum fluctuations that seeded our universe were not formless noise. They were specific vibrations in the fundamental entities that make up reality, entities known as quantum fields. We have focused on the inflatoned field, the primary driver of that explosive expansion, but it was not alone. The cosmos is a symphony of fields, each with its own properties and particles. The electron field gives us electrons, the quark field gives us quarks, and the Higgs field gives mass to fundamental particles. All of these fields were present in the fiery dawn, and all of them were subject to the same restless quantum jitters. While the inflaton's fluctuations were stretched into the dominant pattern of density, the tremors in these other fields could have left their own, more subtle signatures on the cosmos. One of the most profound possibilities involves the gravitational field itself. According to Einstein, gravity is the curvature of spacetime. In the quantum realm, this means spacetime itself should fluctuate. During inflation, these quantum tremors in the fabric of reality would have been amplified into vast, undulating waves moving at the speed of light. These are primordial gravitational waves, ripples in the very geometry of the universe, created in that first unimaginable moment. They are not like the gravitational waves we detect from colliding black holes today. Those are recent, specific events. Primordial waves are a fossil hum, a background sea of spacetime ripples from the birth of everything. And we might just know how to find them. These waves would have left a unique, twisting fingerprint on the polarization of the cosmic microwave background light, a pattern physicists call B-modes. Finding this signature is one of the holy grails of modern cosmology. It would be a direct, smoking gun confirmation of inflation, and more than that, it would act as a cosmic thermometer. The strength of these waves tells us the energy scale of the universe during inflation, offering a glimpse into the realm where gravity itself becomes quantum. It is a bridge to the Planck epoch. Beyond gravity, fluctuations in other quantum fields could hold the keys to other great mysteries. Take dark matter. What if it is not a single particle, but a particle born from the vibrations of its own unique quantum field in the early universe? A specific type of fluctuation could have generated these particles in vast abundance, cold and stable, ready to form the invisible scaffolding we discussed. Or consider the greatest asymmetry of all. Our universe is made almost entirely of matter, with very little antimatter. Why? A process called baryogenesis must have favored the creation of matter over antimatter in the early cosmos. This imbalance could have been driven by the dynamics of quantum fields, their fluctuations and decays subtly tipping the scales in favor of the protons and neutrons that would later build stars and planets. So when we speak of those initial quantum seeds, we are not talking about a single note, but a rich chord struck across the entire spectrum of reality. The inflaton's hum gave us the large-scale structure, but the quieter harmonies from other fields may have dictated the cosmic composition, filling the universe with dark matter and ensuring there was ordinary matter left to shine. This quantum field landscape is the true bedrock of existence, and its faintest vibrations wrote the first draft of everything we see. But how can we possibly test a story that spans from a quantum whisper to a galactic supercluster? We cannot rewind the universe and run it again with different settings. Yet, in a profound twist, we have found a way. We build our own. Inside the world's most powerful supercomputers, scientists are performing the ultimate experiment in cosmic history. They are creating entire universes from scratch, not with telescopes but with lines of code. This is the realm of computational cosmology. The process begins with a single, elegant assumption. The scientists program the initial conditions not as a smooth, blank slate, but as a specific mathematical pattern called a Gaussian random field. This is the precise statistical fingerprint predicted for quantum fluctuations stretched by inflation. It is a digital canvas painted with the exact type of random, microscopic hills and valleys we have been discussing. Onto this canvas, they impose the immutable laws of physics. The relentless pull of gravity, calculated across billions of virtual particles representing dark matter. The complex fluid dynamics of ordinary gas as it heats, cools, and collapses. The explosive feedback from supernova and the voracious appetites of supermassive black holes. Then they press start. For weeks or months, the supercomputer labors, simulating the passage of over 13 billion years in a breathtakingly accelerated digital dance. What emerges is nothing short of miraculous. From that initial field of random numbers, a familiar structure begins to coalesce. Filaments of dark matter snake across the void. At their intersections, dense halos form. Gas flows in, ignites into virtual stars, and gathers into shimmering galaxies. These galaxies, in turn, arrange themselves into a vast, intricate cosmic web, complete with great empty voids and dense, rich clusters. Projects with names like the Millennium Simulation and Illustris TNG have produced these breathtaking virtual universes. And when astronomers compare these digital creations to the actual maps produced by galaxy surveys like the Sloan Digital Sky Survey, the agreement is staggering. The large-scale distribution, the statistical properties of galaxy clusters, the very architecture of the web, they all match our observed reality with uncanny precision. This is not a trivial result. The simulation is not programmed to look like our universe. It is programmed to follow the rules of physics starting from a specific, quantum-inspired seed. The fact that this process naturally yields a cosmos that looks like our own is a powerful, albeit indirect, validation of the entire story. It tells us that if you start with the kind of random fluctuations inflation predicts, and let gravity and known physics work for billions of years, you get us. These simulations are more than just confirmations, they are digital laboratories. Scientists can now run experiments impossible in reality. What if dark matter was slightly warmer, moving faster in the early universe? Run the simulation and see how galaxy formation is suppressed. What if the initial fluctuations were a little stronger or followed a different statistical pattern? The cosmic web that forms looks distinctly alien, failing to match the delicate tapestry we observe. By tweaking these fundamental parameters, cosmologists can test which ingredients are essential to cook up a universe like ours, and which would lead to a cosmic dead end. In this way, the quantum seeding hypothesis moves from a beautiful idea to a robust, testable framework. The virtual galaxies shining on supercomputer screens are the ghostly echoes of those first quantum tremors, grown to maturity in a world of silicon and logic, whispering that we are on the right path to understanding our own spectacular origins. The ultimate test of our cosmic origin story is written in the light we have yet to collect. Our understanding of quantum seeding is not a closed book, but a hypothesis poised for its most rigorous examination, one that is now driving the creation of instruments of almost unimaginable power. We are on the cusp of a new golden age of observational cosmology, where next-generation telescopes will look deeper, map wider, and measure more precisely than ever before, each one designed to interrogate a different chapter of this grand narrative. Take the James Webb Space Telescope. Its primary mission is to stare back into the cosmic dawn, to capture the faint, red-shifted glow of the very first galaxies and stars. By studying their shapes, their sizes, and how they are clustered, Webb provides a crucial reality check. Do these infant galaxies match the predictions of our models that start with quantum fluctuations and cold dark matter? Their properties are a fossil record of the earliest stages of gravitational growth, offering a direct window into how those initial seeds first sprouted into luminous structure. While Webb looks at the first brilliant endpoints, the Vera C, Rubin Observatory, with its gigantic mirror and colossal camera, will conduct the ultimate cosmic census. From a mountaintop in Chile, it will scan the entire southern sky every few nights for a decade, cataloging the positions and distances of billions of galaxies. This map will be so exquisitely detailed that it will reveal the cosmic web in higher definition than we have ever seen. It will measure the Baryon acoustic oscillation scale, that fossilized sound wave, with such precision that we can trace the expansion history of the universe and the growth of structure with unprecedented accuracy. tightening the constraints on our origin story from the other end of time. And then there are the probes designed to read the opening lines themselves. Space-based missions now in development, like Lightbird, have one supreme goal. They will measure the polarization of the cosmic microwave background with a sensitivity far beyond any previous experiment. They are hunting for that elusive, curling B-mode pattern, the signature of primordial gravitational waves generated during inflation. Detecting that faint twist in the oldest light would be a direct observation of quantum tremors in spacetime itself, a smoking gun for the inflationary epoch and a measurement of its energy scale. Each of these new datasets does more than add details. They allow scientists to perform a profound statistical audit on the universe's birth certificate. By analyzing the distribution of galaxies and the patterns in the ancient light with this new precision, cosmologists can measure the statistical properties of the initial quantum fluctuations with forensic detail. Are they perfectly Gaussian, the bell curve of pure randomness, as simple inflation predicts, or will we find subtle deviations, faint hints of non-Gaussianity? Such a discovery would be revolutionary. It would indicate that the physics of the very early universe was more complex, that interactions between quantum fields during inflation left a unique fingerprint in the seeds. It could point the way to entirely new forces or particles at play in that first fleeting moment. We are no longer just reconstructing a story from ancient evidence. We are building the tools to interrogate the first page of cosmic history with a clarity our predecessors could only dream of, ready to listen for the echoes of creation with entirely new ears. Our own galaxy, a majestic spiral of hundreds of billions of stars, is the direct descendant of a specific, random tremor in the quantum field. This is a humbling and awe-inspiring thought. It means the grand cosmic architecture we inhabit, with all its lawful beauty, rests on a foundation of fundamental chance. There was no blueprint for the Milky Way, no cosmic architect who sketched its spiral arms in advance. Its seed was one possibility among an infinite number of others, a microscopic roll of the quantum dice that happened to occur in our particular patch of the inflating universe. This intertwining of randomness and law is the central philosophical tension of our origin story. The process is not lawless. Once those random seeds were frozen into existence, the deterministic machinery of physics took over. Gravity's relentless pull, the dynamics of dark matter, the nuclear fusion in stars, all followed precise, predictable rules. The universe is a place of magnificent order, but that order blossomed from an initial state of pure quantum probability. It is as if the universe were given a set of perfect, unwavering laws and a completely random starting configuration, then set free to evolve. The breathtaking structures we see are the inevitable consequence of those laws acting upon that specific random input. This challenges some of our deepest intuitions about design and destiny. For centuries, the remarkable order and fine-tuning of the cosmos have been seen by some as evidence of intentional creation. Yet here, science reveals a different narrative. The fine-tuning may not be in the initial conditions, but in the laws themselves. The laws of physics are exquisitely precise. If the strength of gravity or the nuclear forces were even slightly different, stars and galaxies could not form, and we would not be here to ponder them. This is known as the Anthropic Principle. In a universe born from quantum randomness, perhaps we should not be surprised to find ourselves in a rare region where the dice fell just right for complexity and life to emerge. Our existence is not proof of a plan, but a consequence of the fact that in a vast or even infinite multiverse of possibilities, some outcomes will, by sheer statistics, allow for observers. This shifts the question from why is the universe fit for life to why are we in the part of the universe that is. It places our home galaxy and our presence within it within a staggering new context. We are not the predetermined pinnacle of creation, but we are also not a mere accident. We are the lawful, beautiful, and statistically rare flowering of a particular quantum possibility. Every star we see at night, every distant galaxy in our telescopes, is a reminder of that profound partnership between chance and necessity, a collaboration that has woven randomness into the very fabric of the cosmic web. Our own existence becomes a curious clue within the cosmic mystery. If those initial quantum whispers had been even a fraction louder or softer, the universe we know would be unrecognizable. A slightly stronger pattern of fluctuations would have created a cosmos far more violent and dense. Gravity would have worked overtime, pulling matter into enormous black holes or causing galaxies to merge in constant, catastrophic collisions long before stable solar systems could ever form. On the other hand, a slightly weaker pattern, a universe born too smooth, would have left gravity with almost nothing to grasp. Matter would have remained spread thin, stars might never have ignited, and the cosmic dark age could have stretched on forever in an empty, sterile expanse. In either of those alternate realities, there would be no planets, no chemistry complex enough for life, and certainly no observers to wonder about their origins. This simple but profound observation leads us to the Anthropic Principle. It is the idea that we, as conscious beings, can only find ourselves in a universe that has the right conditions to allow for our existence. We are, in a sense, selecting the outcome by our very presence, the specific random roll of the quantum dice that led to our cosmic web was not predetermined to be special. But it was, by necessity, one of the rolls that allowed for the long, intricate chain of events that leads from a density fluctuation to a living, thinking creature gazing at the stars. This principle provides a powerful, if sometimes unsettling, framework for understanding the peculiar fine-tuning we see. Why do the fundamental constants of nature seem so perfectly calibrated for complexity? Why is the strength of gravity just right to allow for galaxies that live for billions of years? The anthropic answer, especially within a multiverse context, is elegantly statistical. If an endless number of bubble universes exist, each with different physical laws and different patterns of quantum seeds, then most of them will be stillborn or barren. But a tiny fraction, by sheer chance, will have the golden combination. And in those rare bubbles, observers will eventually arise and ask why their home seems so uniquely hospitable. We are not at the center of creation, but we are necessarily in one of its habitable neighborhoods. This links the vast, impersonal machinery of quantum cosmology directly to the intimate fact of our own awareness. It suggests that the story of the galaxies is also, in the end, a story about the possibility of witnesses. The quantum noise that painted the cosmic web did not have us in mind, but it accidentally created a canvas where beings like us could one day appear and trace our lineage back to its first faint brushstrokes. The quantum seeds for our galaxies are real, but their ultimate origin remains one of the deepest enigmas in all of science. We have traced their journey from microscopic tremors to cosmic superstructures, yet we must now confront the profound question of where those tremors themselves came from. What was the source of the initial randomness? The inflationary model brilliantly explains how quantum fluctuations were stretched into galactic seeds, but it does not explain why those fluctuations existed in the first place. This inquiry pushes us to the very edge of our understanding, to a moment before time as we know it began. The classical Big Bang model describes a singularity, a point of infinite density and temperature where the equations of general relativity break down completely. It is a boundary, a wall beyond which our current physics cannot see. To peer beyond that wall, we must move from cosmology to quantum cosmology, a field that attempts to apply the strange rules of the quantum world to the universe as a whole. Here, physicists propose that the entire cosmos, in its earliest state, could be described by a wave function. This is not a wave in space, but a wave of probability for the universe itself. In this framework, one compelling possibility is that our universe did not emerge from a singular explosion from nothing, but from a quantum tunneling event. Picture a hill. On one side is a state of true nothingness, not even space or time. On the other side is a tiny, nascent universe. According to quantum mechanics, there is always a non-zero probability that a system can tunnel through a barrier it classically could not cross. In this cosmic sense, the universe could have tunneled from nothing into something, a spontaneous emergence from the quantum vacuum of a more fundamental reality. In such a genesis, the initial quantum fluctuations were not imposed from outside. They were inherent to the birth process itself, the inevitable quantum jitters imprinted on the infant universe as it flickered into existence. This leads to an even more mind-bending possibility. If the universe has a wave function, then there may not have been a single, definite beginning, but a spectrum of possibilities. The specific configuration we see, with its particular pattern of seeds, might be just one likely outcome from a quantum superposition of many potential starting states. Our entire cosmic history, with all its galaxies and stars, could be the result of a single quantum trajectory that was actualized out of a haze of probability. This is why the quest to understand galactic seeds is so much more than an astronomical puzzle. It is a direct pathway to the mystery of existence. The pattern frozen into the cosmic microwave background is more than a blueprint for structure. It is a fossil from the first moment of reality, carrying information about the quantum birth of spacetime. To decode it fully, we require a theory of quantum gravity, a framework that successfully marries the large-scale physics of Einstein with the subatomic rules of quantum mechanics. This is the holy grail of modern physics, pursued through theories like string theory and loop quantum gravity. These approaches suggest that at the Planck scale, the concepts of a singular beginning and smooth spacetime dissolve, replaced by a foaming, discrete geometry. In such a picture, the fluctuations that seeded galaxies might be the amplified remnants of the quantum graininess of spacetime itself. The seed of every galaxy, therefore, may hold the key to the origin of everything. By studying the largest structures in the sky, we are indirectly probing the smallest possible scales of reality, seeking the fundamental laws that allowed anything at all to be. That quantum dice roll at the beginning of time was more than a random tremor. It was a message. An intriguing modern perspective suggests we view the entire universe not just as a collection of matter and energy, but as a vast information processing system. From this viewpoint, those initial quantum fluctuations were not merely random jitters in a field. They were the universe's first bits of data, pure, unpredictable ones, and zeros generated by the fundamental uncertainty of reality. Inflation acted as a cosmic amplifier and encoder, taking this raw, random information and stretching it, imprinting it permanently onto the density field of the cosmos. The pattern of hot and cold spots in the ancient microwave background, that is the universe's first hard drive, a fossilized data storage medium holding the initial conditions. But information that is merely stored is inert. The true magic happened in what came next. The subsequent 13.8 billion years of gravitational clustering, of dark matter scaffolding and gas collapse can be seen as an immense slow-motion computation. The laws of physics, gravity, thermodynamics, nuclear processes are the algorithms. They take that initial, simple data string of random bits and process it, step by step, over cosmic time. Through nonlinear interactions and feedback loops, this processing transforms the simple input into an output of breathtaking complexity, the intricate cosmic web with its galaxies, clusters, and voids. The universe, in a very real sense, computed its own structure. This computational perspective leads to even deeper, more speculative connections. Some theoretical physicists are exploring a radical idea that spacetime itself, the very stage upon which the cosmic drama plays out, may be an emergent property of quantum information. In particular, the phenomenon of quantum entanglement, the spooky connection between particles that Einstein famously disliked, might be the fundamental glue from which the geometry of space is woven. Under this hypothesis, the dense network of entanglement links in the early universe could have directly given rise to the connectivity of the cosmic web. The filaments that link galaxies might be shadows of an underlying quantum network, a hidden architecture of information that predates space itself. This is not settled science, but a frontier of thought that synthesizes cosmology, quantum gravity, and computer science. It frames the entire history of the cosmos as a single, grand computation. The initial quantum data was the input, the unbreakable laws of physics were the program. And after a runtime of billions of years, the output is the galaxy-filled sky we observe tonight. It is a compelling narrative that suggests the universe is not just something that contains information. In a very profound way, it is information being processed into ever more complex and beautiful forms. This scientific narrative of order from chaos is not entirely new to the human imagination. Long before telescopes or particle accelerators, our ancestors gazed at the stars and told stories of how it all began. From the swirling, formless chaos of ancient Greece to the yawning, primordial void of Ginnungagap in Norse mythology, cultures around the world envisioned creation as a process of shaping, of bringing structure out of an initial state of undifferentiated potential. These myths are more than quaint fables, they are profound expressions of a fundamental human question. Where did the world come from? How did something come from what seems like nothing? In this light, our modern cosmological story emerges as the latest chapter in humanity's oldest epic. It is a scientific creation myth, one that replaces gods and monsters with quantum fields and gravitational laws, yet retains the same core archetype. We still tell of a beginning from a formless, energetic state. We still describe a catalyst that sparks differentiation. The difference is in the details, and those details are what make our current understanding so revolutionary. In the old stories, order was often imposed by an external, conscious force, a deity speaking light into the darkness or a hero slaying a chaos monster. Our scientific myth reveals something far more intimate and awe-inspiring. The chaos of the early universe was not a malevolent force to be tamed. It was the quantum vacuum, a state of pure, seething potential, governed by probability and uncertainty. And the order that emerged was not commanded from the outside. It was generated from within by the universe's own intrinsic properties. The quantum fluctuations were not an external intervention. They were an inevitable feature of reality at its smallest scales. Gravity was not a divine sculptor, but a fundamental force inherent to energy and mass. The entire majestic process, from the first whisper to the last spiral galaxy, unfolded according to immanent, unbreakable physical laws. This perspective is both deeply humbling and strangely empowering. It humbles us because it removes any special, preordained place for our galaxy or our species. We are the result of a particular random draw in a cosmic lottery. Yet it empowers our understanding because it places the genesis of everything we see within a comprehensible, testable framework. We are not passive subjects of a mysterious creation. We are the universe itself, grown complex enough to look back and trace the chain of causality that led to its own reflection. Our scientific myth does not answer every philosophical question about why there is something rather than nothing. But it provides a breathtakingly coherent account of how that something, once it existed, could weave itself into the tapestry of stars we call home. It connects our most ancient wonder directly to the light of the oldest sky, telling us that in seeking the origin of galaxies, we are also rediscovering one of humanity's oldest and most enduring stories. A perfectly calm lake under a moonless sky offers a profound image of cosmic beginnings. That glassy, undisturbed surface mirrors the universe's initial state of near-perfect smoothness, a vast, featureless expanse holding immense potential. But even the most placid water is never truly still at the molecular level. Minute currents and collisions create microscopic turbulence, causing faint, unpredictable ripples to flicker across the surface. These are our quantum fluctuations, the random, subatomic jitters imprinted on the fabric of reality itself. They are the universe's faintest whisper of imperfection. Now envision something impossible happening to that lake. Instead of a breeze or a thrown stone, the entire body of water begins to expand at an incomprehensible rate, its surface stretching in every direction simultaneously. Those fleeting, microscopic ripples are caught in this cosmic stretch. They do not fade away. Instead, they are pulled apart, magnified, and frozen into the very geometry of the now vast lake, transformed from ephemeral tremors into permanent, rolling waves of varying height. This is inflation, the ultimate amplifier, locking quantum chance into a classical, cosmic-scale blueprint. For eons, a new force begins to work. A gentle, persistent wind blows steadily across the water, a force representing gravity. It does not create new waves, but it responds to the landscape that already exists. The wind pushes water from the troughs up toward the peaks of those frozen waves. Slowly, inexorably, water accumulates at the high points. The peaks grow taller and more distinct, while the valleys between them become deeper and emptier. Over cosmic time, these accumulations separate into vast, distinct bodies of water, isolated from one another by stretches of exposed lakebed. These are our galaxies and clusters, the great islands of matter in the sea of space, each one tracing its origin back to a specific peak in that initial, amplified ripple pattern. This metaphor, while a simplification, captures the essence of the story. It visualizes how a pattern born from randomness can, through a powerful transformative process and a persistent shaping force, give rise to a structured, magnificent whole. The universe did not begin with galaxies sketched in the stars. It began with a quiet lake and the faintest of ripples, setting in motion a chain of events that would sculpt the cosmos. The universe's biography is written in light, gravity, and time. To truly grasp the journey from quantum whisper to galactic city, we must walk its chronological path from the first unimaginable fraction of a second to the present moment. Our story begins not with a year or even a second, but with a time so brief it has no name in our language. At 10 to the power of negative 36 seconds after the beginning, the cosmos was a seething, microscopic realm. Here, in the heart of the inflationary epoch, the inflattened field dominated reality, and within that field, the fundamental uncertainty of quantum mechanics played out. Random fluctuations, tiny hills and valleys of energy, flickered into and out of existence. These were not yet structures. They were mere possibilities, ghostly tremors in the newborn fabric of everything. But they would not remain ghosts for long. By the time the universe was just 10 to the power of negative 32 seconds old, something monumental happened. Inflation, that period of hyper-accelerated expansion, came to an end. In that fleeting instant, the universe had doubled in size over and over again, stretching by a factor of at least 10 to the power of 26. This cosmic stretch did something irreversible to those quantum jitters. It yanked them from the subatomic world and inflated them to scales larger than galaxy clusters. A fluctuation that lasted for a moment was pulled so far, so fast, that it could no longer snap back. It was frozen, transformed from a quantum maybe into a permanent classical fact, a slight variation in the density of matter and energy etched across the cosmos. The blueprint was now set, a faint pattern of potential waiting in the darkness. For nearly 400,000 years, the universe expanded and cooled from an opaque, seething plasma. Then, at that precise moment, atoms formed. protons and electrons combined into neutral hydrogen and the fog cleared. For the first time, light could travel freely. That first flash, released into the expanding cosmos, is what we detect today as the cosmic microwave background. This ancient glow is not a uniform sheet of light. Its subtle temperature variations, those hot and cold spots, are a direct photograph of those density variations imprinted by inflation. When we look at that map, we are staring at the universe's baby picture, seeing the amplified quantum seeds frozen in time. The stage was set, but the actors were not yet in place. For almost 100 million years, the cosmos entered a dark age. The ordinary hydrogen gas was quiet, but the invisible dark matter, already pooled within the densest peaks of that primordial blueprint, was silently sculpting the future. Within these deepening gravitational wells, gas finally began to collapse. Around 1 to 200 million years after the Big Bang, in the hearts of the most pronounced dark matter halos, the first stars ignited. These were not gentle suns, they were behemoths, hundreds of times the mass of our own, and their fierce ultraviolet light began to tear apart the surrounding atomic fog, ending the cosmic dark age in a blaze of glory. These first stellar nurseries were the kernels of the first galaxies. Over the next billion years, gravity's patient work continued. These proto-galaxies, each born from its own density peak, began to dance. Drawn together by their mutual attraction, they merged and cannibalized one another, growing in size and majesty. This era of assembly built the foundations of the large-scale cosmic web we see today. Our own galactic home has its own specific chapter in this story. Roughly 9 billion years after the Big Bang, after a long history of mergers and the steady accretion of gas, the Milky Way settled into its familiar spiral form. A graceful disk of stars, gas, and dust rotating around a central bulge, its structure a testament to a relatively quiet and orderly growth within its filament of the cosmic web. And now here we are at 13.8 billion years. We look out with our telescopes and see a universe populated by hundreds of billions of galaxies, each a majestic island of stars. From the tiniest dwarf galaxy to the largest cluster, every single one can trace its lineage back through time, through the first stars, through the silent guidance of dark matter, through the snapshot of the ancient light, all the way back to those specific, random quantum jitters in the first sliver of a second. This timeline is not just a sequence of events, it is our origin story, connecting our place in the cosmos directly to the universe's first and most fundamental breath. That ancient pattern of hot and cold spots is not just random. It follows a precise mathematical rule, a signature that was predicted decades before we had the technology to find it. This rule is known as the Harrison-Zeldovich Spectrum, and its discovery in the cosmic microwave background was a moment of profound confirmation. The concept is called scale invariance. In simple terms, it means the universe's initial wrinkles looked roughly the same no matter what size you examined. Whether you were looking at a patch of sky destined to become a single galaxy or a region that would evolve into a supercluster of thousands of galaxies, the amplitude of the initial density variation was almost identical. This is a very specific and non-obvious prediction. If the seeds for structure had come from a cataclysmic event like a phase transition or the decay of exotic particles, you might expect one preferred size to dominate. You would see more fluctuations at a specific scale, like waves in a pond mostly having one wavelength. But that is not what we observe. The cosmic microwave background shows a symphony of fluctuations across all scales, from the very large to the very small, with no single note overpowering the others. Why is scale invariance the expected outcome of quantum fluctuations plus inflation? It stems from the unique nature of the process. Quantum fluctuations are inherently random and have no preferred scale. They are like the static on an old television, a hiss of equal power across all frequencies. Inflation then acts as a universal amplifier. As space expands exponentially, it stretches every fluctuation, regardless of its original size, by the same enormous factor. A tiny quantum jitter and a slightly larger one both get blown up to cosmic proportions, preserving their relative amplitudes. It is like taking a piece of graph paper with a fine, random pattern and enlarging it to the size of a billboard. The pattern looks the same, only the absolute scale has changed. This creates a nearly scale invariant spectrum, a mathematical fingerprint of a quantum origin stretched by exponential expansion. For cosmologists, finding this precise pattern in the sky was the equivalent of a detective matching a suspect's fingerprint at the scene of a crime. Projects like the Planck satellite did not just map the hot and cold spots. They performed a detailed statistical analysis, measuring the power of the fluctuations at every angular size. The data points fell almost perfectly on the curve predicted by the simplest models of inflation. This quantitative match is what elevates the theory from a compelling idea to the foundational framework of modern cosmology. Any alternative theory for the origin of cosmic structure must now also reproduce this specific scale-free pattern, a very high bar to clear. This mathematical rule, born from the marriage of quantum uncertainty and exponential expansion, is now etched into our understanding of the cosmos. It tells us that the universe did not receive its structure from a single dramatic event, but from a democratic process where every scale of fluctuation had an equal voice in shaping the future. The blueprint for a galaxy and the blueprint for a supercluster were written with the same faint quantum ink. The cosmic web is not a static monument. It is a living, evolving structure, and its future is shaped by a force more mysterious than dark matter. Dark energy, the enigmatic driver of the universe's accelerating expansion, is now the dominant architect of our cosmic destiny. For billions of years, gravity was the great sculptor, pulling matter together into the magnificent filaments and clusters we see today. But around 5 billion years ago, a cosmic tipping point was crossed. The repulsive push of dark energy began to overcome the attractive pull of gravity on the largest scales. This is not a local event. It is a fundamental change in the behavior of spacetime itself, and it is rewriting the final chapters of our galactic story. Imagine the cosmic web as a vast, intricate tapestry. Dark energy is not tearing the threads apart. Instead, it is steadily stretching the loom on which the tapestry is woven. The space between the great filaments and superclusters is growing at an ever-increasing rate. Galaxies that are not already bound together by gravity's intimate embrace are being carried apart on this accelerating flow of space itself. They are not moving through space, they are becoming separated because the space between them is literally generating more of itself. Over the next tens of billions of years, this will lead to a profound isolation. Galaxy clusters, the densest knots in the web, are gravitationally bound islands in this expanding ocean. They will continue to merge internally, with smaller galaxies within a cluster cannibalizing each other, eventually forming a few monstrous, smooth, elliptical galaxies. But these clusters themselves will become islands of light in an ever-darkening sea. The threads of the web that connect them will stretch, thin, and eventually fade from view as the galaxies along them are pulled away. For a galaxy like our own Milky Way, the local future is one of merger and then quiet decline. In about 4 billion years, we are destined to collide and merge with our giant neighbor, the Andromeda Galaxy. This spectacular dance will create a new, larger elliptical galaxy, often nicknamed Milkomda. For a time, this merger will trigger a burst of new star formation as gas clouds are violently compressed. But it will also use up much of the available fuel. After that, star formation will slowly sputter out as the remaining gas is either turned into stars or ejected by the intense radiation from aging stellar populations and the supermassive black hole at the galaxy's heart. The brilliant blue-white light of massive young stars will become a rarity, then a memory. The galaxy will redden and dim as its stars age, eventually becoming a quiet realm of red dwarfs, white dwarfs, and neutron stars. This is the fate awaiting most galaxies that are not in rich clusters. They will consume their gas, finish their star-forming lives, and enter a long, slow fade. On timescales so vast they defy human intuition, hundreds of billions of years into the future, the observable universe will become a very different place. Because of the accelerated expansion, light from galaxies not already in our gravitationally bound local group will eventually be stretched beyond the point of detection. Their photons will redshift into oblivion. To any future astronomers in Milkomda, the sky will appear nearly empty, save for the faint, aging stars of their own galaxy. The grand cosmic web, with its brilliant filaments and clusters, will have vanished from their view. It will be a lonely, diffuse cosmos, yet the legacy of the quantum seeds is permanent. The pattern they imprinted, that specific arrangement of hills and valleys in the density of the universe, will never be erased. It will simply fade into a different kind of fossil. The stellar remnants, the dark matter halos, even the supermassive black holes at galactic centers, will still trace out that original architecture. The distribution of these dark, silent objects will forever hold the ghostly imprint of the universe's first moment. The future cosmos, for all its darkness and isolation, will remain a recognizable, if faded, reflection of its quantum origins. The story that began with a whisper in the void will end with that whisper etched into the ultimate stillness, a testament to the enduring power of a random tremor at the dawn of time. The quest to understand galactic seeds forces us to confront a beautiful truth about the universe. Its largest structures and its smallest particles are not separate stories, but different chapters of the same book. The inflaton field, that mysterious energy that drove the universe's explosive growth, is not a cosmic oddity. It is a close cousin to fields we study in particle accelerators here on Earth, like the Higgs field that gives other particles their mass. This means the energy scales that shaped the entire cosmos might one day be within our reach, not just by looking at the sky, but by peering into the heart of matter. The search for the seeds of galaxies is, in a very real sense, a search for new physics. To truly grasp those initial quantum fluctuations, we need the language of quantum field theory, the same mathematical framework physicists used to describe quarks, electrons, and the forces that bind them. This creates a profound collaboration. Cosmologists look out at the ancient sky and see the end result of a primordial process. Particle physicists, working with massive machines like the Large Hadron Collider, recreate the extreme conditions of the early universe on a microscopic scale. Each group provides clues the other desperately needs. A discovery in a detector deep underground, perhaps a new particle that could be dark matter, immediately reshapes our models of how the cosmic web formed. Conversely, a precise measurement of the cosmic microwave background, like the pattern of those primordial gravitational waves, tells particle theorists the energy their equations must match. It is a two-way street of discovery. The majestic spiral of a distant galaxy is not just an astronomical object. It is a cosmic message, a fossilized data point from an era of unimaginable energy. By studying its origin, we are conducting the ultimate experiment, using the universe itself as our laboratory. The arrangement of galaxies across billions of light years becomes a testing ground for the laws that govern reality at scales a billion times smaller than an atom. This synergy is more than convenient. It is a powerful engine for human understanding, revealing that the cosmos is a unified, coherent whole. The same fundamental rules paint the swirl of a galaxy and dictate the dance of a subatomic particle, reminding us that in seeking the origin of the stars, we are also uncovering the deepest nature of reality itself. The majestic cosmic web is not a secret kept behind laboratory doors. Its story belongs to anyone with curiosity and an internet connection. Across the world, hundreds of thousands of people have become active explorers in this grand narrative, not by peering through telescopes, but by looking at their computer screen. Projects like Galaxy Zoo have transformed galaxy classification from a task for a few dozen astronomers into a global, collaborative effort. This is citizen science, and it has revolutionized how we understand the diverse family of galaxies that grew from those quantum seeds. When you log into such a project, you are presented with a stunning, real image from a sky survey like the Sloan Digital Sky Survey. Your task seems simple. Is this galaxy a graceful spiral, a smooth elliptical, or an irregular merging system? You click, you move to the next one, but that simple act is profound. You are not playing a game. You are processing data that even the most advanced computer algorithms can struggle with. The human brain's exceptional pattern recognition is helping to sort the universe, one galaxy at a time. Every single classification becomes a valuable data point in a massive statistical study. Researchers use this crowd-sourced data to answer fundamental questions. How common are spiral galaxies versus elliptical ones at different distances, and thus at different cosmic times? How do galaxy collisions shape their final forms? Each click helps trace how a galaxy's destiny, set by its initial quantum seed and local environment, plays out over billions of years. By participating, you see the direct, stunning results of that ancient process. You witness the elegant spiral, its arms likely tracing density waves in an orderly disk that formed from a quiet seed. You see the featureless elliptical, the product of a busy cosmic neighborhood or a violent merger that scrambled stellar orbits. You might even catch two galaxies in a slow, gravitational dance, their shapes distorted as they merge into something new. This turns abstract theory into a tangible, human-scaled experience. It demystifies the science, revealing it as a process of careful observation and collective discovery, not just complex equations. It fosters a deep, personal connection. When you look up at the night sky, you might now know that you have personally helped catalog the very kinds of structures you are gazing upon. You have become part of the story, helping to read the universe's own biography, written in starlight and shaped by a whisper from the beginning of time. The universe did not spring from a philosophical void of absolute nothingness. This is a crucial point where the poetry of popular science often collides with the precision of physics, and the distinction matters. When cosmologists speak of quantum fluctuations emerging from the quantum vacuum, they are not describing a magical creation from a state of non-existence. The quantum vacuum is a very specific physical concept. It is the lowest possible energy state of a quantum field, but it is far from empty or inert. Think of it as the calmest possible sea, yet beneath that calm surface, the water is alive with ceaseless, churning motion. Particle and antiparticle pairs constantly flicker in and out of existence, borrowing energy from the uncertainty principle itself. This vacuum is a dynamic medium brimming with potential, and it operates under the strict mathematical laws of quantum mechanics. The fluctuations that seeded our galaxies were not miracles. They were the inevitable statistical ripples in this active, law-governed substrate. They were perturbations in something that already existed, following rules that were already in place. This transforms the narrative from one of inexplicable magic to one of profound transformation within a pre-existing framework of physical reality. Similarly, the idea that the Big Bang violates the conservation of energy is another common misunderstanding. Energy conservation is a sacred principle in physics, and our best models suggest the universe has upheld it from the very beginning. The total energy of the cosmos appears to be remarkably close to zero. How can that be when we see a universe filled with galaxies, stars, and light? The secret lies in gravity's unique ledger. All the positive, luminous mass energy you see in stars and planets is nearly perfectly balanced by a vast reservoir of negative gravitational potential energy. Imagine constructing a skyscraper. Lifting materials against Earth's gravity requires work storing energy in the system. In cosmology, assembling matter from a smooth, spread-out state into dense clumps like galaxies similarly stores negative gravitational energy. In the simplest models, these two immense sums cancel each other out. So the universe could, in principle, have begun with a net energy of zero, with all the positive energy we observe today being offset by the negative gravitational binding energy of its own structure. This is not a philosophical trick. It is a rigorous, if deeply counterintuitive, feature of general relativity. The process described by inflation and quantum seeding is not a violation of physical law, but a breathtaking demonstration of its consistency on the grandest possible stage. It replaces the mystical idea of creation from nothing with a scientific narrative of transition. A highly energetic, unstable state of a quantum field transformed, through a cascade of well-understood physical processes, into the expanding, cooling, structured cosmos we inhabit. The awe we feel should not come from a breach of the rules, but from the staggering beauty and coherence of the rules themselves. They allowed a universe of such complexity and grandeur to unfold from such a simple, elegant, and lawful beginning. Look up on a clear, dark night. That sea of stars, the faint, misty band of the Milky Way, the profound blackness stretching between them, it all feels eternal and separate from our daily lives. Yet that entire cosmic vista, in its every detail, is the direct and magnificent echo of a quantum whisper. Every single point of light you see exists because of a specific, random fluctuation that occurred when the universe was less than a trillionth of a second old. That speck of light might be a star like our Sun, born from a cloud of gas that collapsed under gravity's pull, a pull that began because a microscopic region of space, by pure chance, had a tiny bit more density than its surroundings. That faint, fuzzy smudge could be another galaxy, an island of billions of stars, tracing its lineage back to its own unique quantum seed. Even the vast, empty voids, the great stretches of darkness, are part of the pattern. They are the low points, the troughs in that initial ripple, regions where matter was subtly thinner, destined to become the great deserts of the cosmic web. This is not a metaphor. It is our physical history, the calcium in your bones, the iron in your blood, the oxygen you breathe. Every atom in your body heavier than hydrogen and helium was forged in the heart of a star. That star itself ignited because gravity gathered material from one of those primordial overdensities. You are literally made of stardust, but that stardust exists because of quantum chance. Your very existence is a link in an unbroken chain that stretches back through supernova explosions, through the first generation of stars, through the silent guidance of dark matter, through the flash of light captured in the cosmic microwave background, all the way to a random tremor in the inflattened field at the dawn of everything. This realization carries a unique kind of awe. It is not the awe of feeling small, but the awe of feeling profoundly connected. The universe is not just a place we inhabit. It is a story we are part of, a dynamic, evolving entity, and the same fundamental processes that sculpted galaxies also set the stage for planets and life. We are not passive observers of a finished cosmos. We are the universe itself, grown complex enough to look back and contemplate its own origins. That night sky is no longer a distant spectacle. It is our family album, and every star is a relative, born from the same ancient, random breath that made our own world possible. Our journey from the quantum foam to the galactic tapestry reveals a universe of astonishing coherence. The rules that govern the tiniest particles are the same rules that orchestrate the grandest cosmic architecture. We have traced a direct line from the random, ghostly jitters in the inflattened field to their explosive amplification during inflation, to their silent shaping by dark matter, and finally to their glorious illumination by the first stars. This is not a collection of separate ideas, but a single, elegant story of transformation. The evidence for this narrative is etched into the sky itself, from the precise pattern of hot and cold spots in the ancient cosmic microwave background, to the vast filamentary web of galaxies we map today, to the virtual universes that emerge from our supercomputer simulations. Together, they form a consistent and compelling picture of our origins. Of course, profound mysteries remain at the very edges of this story. The true nature of the initial singularity, the quest for a complete theory of quantum gravity, and the breathtaking possibility of a multiverse. These are the frontiers where our understanding currently fades into wonder. Yet the core idea that quantum randomness seeded every galaxy stands as one of the most robust pillars of modern cosmology. It teaches us a powerful lesson about interconnection. The cosmos is not a collection of separate realms, the very large and the very small. It is a single, dynamic entity where processes at the scale of a trillionth of a proton set in motion the formation of structures billions of light years across. This connection is not just theoretical, it is woven into the fabric of reality we observe. So the next time you find yourself beneath a clear, dark sky, take a moment to really look. Each point of light, each faint smudge of a distant galaxy, is not just a distant object, it is the magnificent, grown-up legacy of a quantum event from the first moment of time. You are witnessing the final, brilliant act of a story that began with a whisper. If this exploration of cosmic origins expanded your view of the universe, consider subscribing for more journeys into the heart of space mysteries. We would love to hear your thoughts on this profound connection between the quantum and the cosmic in the comments below.